Yes, this is Mr. White.
And Mr. Sadler.
And today we're going to talk about energy, and specifically energy transformations as it relates to roller coasters. So I always talk about my favorite Great America ride. I always talk about the Raging Bull. So go ahead, raise your hand if you have been on the Raging Bull in Gurnee.
I probably have, but it's been a while.
And I like the Raging Bull, of course, because you go really high and you go really fast. And so there's this nice gradual slope where you go up the track, and then there's almost what seems like a straight vertical drop, and then you get to the bottom and you shoot out of the top, go to a second hill, I believe. Okay, and the second hill, by the way, is never as tall as the first hill, which we'll talk about as well. So, Mr. Sadler, we're talking about energy transformations, and at the top of the hill here, so I don't know if we want to label this. Yeah, we'll call this section here point A, because I want to come back to this. We'll call this B.
Okay.
C, D. We'll call that E.
Okay.
All right. Let's talk about point B here.
All right.
What does point B have?
According to this drawing, it has the maximum gravitational potential energy.
Right. It has
Because that's the highest spot.
GPE, we'll call it max.
All right.
And this is, of course, due to its mass, the acceleration due to gravity,
And its height.
and, to be very specific, the maximum height of the roller coaster.
Correct.
Okay? So, this is the energy that you have at the top of the first hill of any roller coaster, is a maximum gravitational potential energy.
Correct.
So my question becomes, when we look at section A here, what is required to give the roller coaster a maximum gravitational potential energy?
Well, the beginning of any roller coaster actually has the lift that raises you to the top, so they're using energy to get you up to that point.
Right, and when we talk about that energy specifically, we're going to talk about the work done by that chain. There's a motor that's dragging you up there, and to give you gravitational energy, then the chain motor has to do work on the roller coaster cars.
Correct.
And then you go screaming down the hill.
Right.
All right, and we talked about this in section 1, high acceleration. All right, that's why we're screaming. And we get to point D, we're at the bottom of the first hill, and actually on the Raging Bull, you're actually underneath the ground. But let's just assume that you are at ground level. What kind of energy do you have there?
Kinetic energy.
And do we want to give that a special label?
Yeah, that's the max there.
Why do you say that?
Well, it's going fastest because it's lost the maximum amount of gravitational potential
Oh,
energy.
yeah.
So whatever the gravitational potential was at the top has now turned into kinetic.
So we have no height,
Correct.
and we have lots of speed.
Correct.
So a maximum kinetic energy at that point. So what do you think's going on at point C?
At point C, there's some difference there's some combination of gravitational potential and kinetic potential. I guess you could say if it's halfway, then they're both half, but there's some portion of gravitational
And some kinetic.
Correct.
And if we were to add the two together,
Absolutely, they have to equal the gravitational at the top,
okay,
and they have to equal the kinetic at the bottom.
because what we're saying due to energy conservation is that the energy at point B and the energy at point D are exactly the same.
Correct.
Could we also say that that would have to be equal to the amount of work we put in?
Absolutely. That's as soon as you drew that, I said to myself, well, I could calculate the work by using point B or point D. I could calculate the work in the lift at A.
Right. So here, we would just be taught the GPE at C plus the KE at C would equal the GPE max
Right.
or the KE max, because they're both the same.
Right.
Talk to me about point E then.
Well, in a perfect world with no friction, I can get up to E because I have energy from B.
Okay.
Okay, but I couldn't get higher than B. But at that point, I'm slowing down. Okay, because I'm coming back up to B where I was 0. So I have some kinetic energy, but I have a lot less.
Okay, so we have some kinetic energy because we're still moving.
Right.
And then we are above the ground, so we must have some GPE. And you said the magic words, in a perfect world where there's no friction, well then, this GPE max, this KE max, this would also be the solution to that problem
Correct.
too, if we were to add it together.
But we know that there's some friction because there's some heat, because there's some loss there.
Because it's reality.
Right.
Okay.
I think we have a loop-the-loop that it's very difficult to get it to go around if you don't get it high enough.
You've got to have it high enough. It's got to have the marble's got to have the right mass, and we'll get that out and show that in class on the loop-the-loop. So there's all sorts of interesting web applets out there and things. So what we're going to show you is we're going to show you something called a FET, and this is called Energy Skate Park. And the FET's really interesting. So let's bring that into the screen here. And so here we have this guy. We're going to show the graph here in a second. We have it set so that there's no track friction. So we're not going to show you that, but there's no track friction. You see, it goes back and forth and back and forth. And the really interesting part here is we can show the bar graph of this. And what you notice is that the total energy stays the same all the time, and it bounces back and forth from kinetic to potential to kinetic to potential, and I love this ability. You can pause it. So when he's at his highest point, he has all potential energy.
Gravitational
Yeah.
potential.
Yeah, and that's gravitational. That's important. When we play it again and pause it at just the right moment, oh, I missed. But you can see he's just outside of the bottom. He has mostly kinetic energy and a low amount of potential.
Well, if you pull this down, I think it'll show that he has.
Oh, that's the
I think
skater.
you can go to 0 there. But it's just because he's still above the ground. Again, it's just a little FET.
So there we go. Oh, that's almost perfect.
Mm-hmm.
Now you see this thermal energy here. This is heat loss due to some friction. So apparently the friction,
We could add it.
we could clear it, so we don't want to see it. And when we play it again, it just bounces back and forth. And because we're at the ground level, the potential actually drops all the way to 0. This is a nice representation of what's actually happening with a roller coaster. And what I like about this is we can actually look at energy versus position. And we can see that graph just go back and forth. So we got the position along the x, we got the energy along the y. We show the different kinds of potential. See the different kinds of potential energy, total, kinetic, and of course the color scheme back and forth. We can get rid of that. And we can also show energy versus time. And this is what my skater's doing. And because we're without friction, it just bounces back and forth, back and forth. And you can actually see
Got the values there.
the color coding and the values for potential and kinetic. You could pause this at any moment in time. You could see, of course, that the energy is the same all the time, just
The total.
the total. And so you got the total energy here. If you add these numbers up, and you go backward to see the same.
It's a
thing.
nice representation of conservation of energy.
Yeah, it's beautiful. Okay, so that's energy transformation. There's nothing new there. I'm going to try and draw something that we've got in your book here on page 366.
So again, it's just like a representation of a roller coaster.
That's not too bad. It's not too good either. A, B, C, D, E, and F for some reason. And what it wants us to do is draw this nice dotted line across here. And first of all, this is possible if there were no friction. It's highly unlikely that the third hill would be higher than the second hill. That's not a likely scenario. But the point of this is, look, we've got all GPE max up here. We know that from before. This is KE max down here. We know that from before. All right? But along this dotted line, okay, we know that the total energy is the same no matter what. So this is some combination of KE plus GPE along this dotted line. And we can do even one better. At this dotted line, so whether we're talking about here, here, or here, what can you tell me about the speed
Speed's
of
the
the roller
same.
coaster? The speed has to be the
Could
same.
even go back to here.
And we could even go back to here. Now, if we were to say, when is the roller coaster most thrilling? You would say, well, the roller coaster is most thrilling there because of the maximum amount of acceleration that you would be getting. Here you're slowing down, but going as fast at point B as you are here.
Right.
Here you're slowing down, but going as fast at this point right here as you were on the first drop. Here it would be exciting as well. So if you had to rank these things, okay, you'd say, oh, well, that's the most exciting, that's the second most exciting. Okay, I would guess that's probably third and then fourth. That's a guess there.
So as I go across, I know the same speed is the same, but if I'm looking for acceleration, I'm looking at where the line is the steepest.
Right. And so, but the speed is the same no matter what. And that's strange. That, okay, we have all these same speeds, but the thrill, of course, comes from the acceleration. Well, then that's when we know that from the last investigation. So, thrilling, not so thrilling, not so thrilling. Okay? And so, how do you solve a problem like this? Well, we keep hinting at it. Look, if you've got gravitational energy at the top and kinetic energy at the bottom, all right, we have to analyze those. And we talked about energy transformations. Well, what we're really alluding to here is energy conservation. Now, let me be clear. On any roller coaster, there is friction. Okay, you cannot escape friction. But there is very low friction on the roller coasters, which is why when it's raining outside, they usually close the roller coasters down because that takes the already low friction. It would make it less for the brakes of the roller coaster.
Right.
So I say energy conservation is the solution here, and that would mean that the change in energy, of course, is zero.
Right.
That the beginning energy would have to be equal to the final energy.
Right.
And so if we go back to either one of my slides, I think this one's a little prettier. At point B, I have a maximum gravitational potential energy, and it's easy to measure height.
Right.
Okay? It's not so easy to measure speed as this thing is racing through the bottom. So how might you find the speed of a roller coaster at the bottom of the first hill? And what, of course, you would have to do is you would have to say, well, at the beginning, there was only gravitational potential energy.
Right.
And at the end, at the bottom of the first hill, there was
Only kinetic.
only kinetic energy. And what you do is you just start subbing in. And you realize that, hey, the mass of the roller coaster doesn't really matter. I can divide by a half because that's easy. I can take the square root of everything because that's easy. And I get the square root of 2gh. Will tell me how fast we're going at the bottom.
Oh, and gravity is a constant, so that makes it easy. So really all I need is the height to find the velocity.
Right. And so the nice thing about this solution is you have seen this before in a completely different context. If we go back to chapter 1, okay, so this was driving the roads. We didn't talk about energy. We talked about velocities and accelerations. We made a lot of distance, velocity, time graphs, etc. Okay, so with all that thought, with all those thoughts in your mind, we had this equation without time. We said the final velocity squared is the initial velocity squared plus 2 times the acceleration times the change in the distance. Well, at the top of the roller coaster, you're not moving.
Right.
And so the speed at the bottom squared is equal to 2 times the acceleration due to gravity times the vertical distance you dropped. And all of a sudden, you see this very familiar solution from the previous slide
Right.
drop out of something we really didn't like. No one really enjoyed those graphs and those kinematics equations. This is verification that what we're doing is correct. If you wanted to find the speed at the top of the second hill, well, you would go through the same exercise. You would say energy initial is the same as energy final. At the beginning, it's only gravitational potential. The maximum at the top of the second hill, well, there's some of each. And so as you hack your way through this,
So really, the kinetic energy is just the drop between the top and the second hill.
Right. And you work your way through this and you realize some things that you've seen this solution time and time again. And I did some algebra in between here. But the kinematic stuff from chapter 1 and the energy stuff from chapters 2 and 3 and now 4 all apply to what we're doing. So there's not really that many kinds of problems. You just have to be able to work your way through the language.
So again, there's more than one way to solve the problem.
Correct. So I believe that covers the green pages for section 2. So signing off, this is Mr. White.
And Mr. Sedler.